thanks. And of course, thanks Marcel, Jean-Philippe, Sulitana for the kind of invitation. So such a pleasure to be here in Cargese, but also to present this work here in this conference. So I will present today the recent work that we are doing about this 3D understand transition with our ultra-cold atoms. So the work is done at the Institut d'Optique. Let me just present the team before going further. So maybe you have met already Yukun and Shudong, which are PhD students, and Niranjan, which is a recent postdoc in the team. And of course, I'm leading the team together with Alain Aspect that you all recognize. We have also theory friend collaborators. So Dominique Deland, we work a lot with him over past year, and unfortunately could not attend the conference. And of course, we are part of the Simon's collaboration of Wave. So you recognize Litana, Marcel, and especially we work with Pierre Pelletier, which is PhD student. So I don't know if he could attend this morning. Okay, so the outline of the talk will be the following. First, I will, since it's not really new that we are studying Anderson localization with ultra-cold atoms, I will try to give you like the status, what it is about the current studies about this Anderson transition, and try to explain you why the experiments were difficult. In the second part, I will present you a new scheme that we have developing over past year, which we call the spectroscopic scheme. We try to load atoms in the disorder with a very well-defined energy and to try to tackle this 3D Anderson transition. And in the last part, I will present some very recent progress that we have on the subject using a new kind of state-dependent disorder that we call the bichromatic speckle. And of course, I will present you what it is. So let me start just very short introduction, as you all heard already. So the field of ultra-cold atom and disorder, let's say, it really started in 2008 with the first observation of Anderson localization in 1D. So that was done in the lens, and also, of course, in our team in Palaiso. And the idea here is to make matter waves, so very cold atoms, and let them propagate in well-controlled disorder potential that you can create with light. And the potential, it just reflects directly the light intensity and divided by detuning so that you can play either attractive or detuning. So there is different kind, of course. You can do bichromatic lattices, you have heard a lot already. You can do laser speckle, where you just shine a laser on a wave plate, you focus on the atoms, and then you have a random pattern of light, which is our favorite disorder potential, and that was mainly used for Anderson localization. And of course, you can do, if you're considering this is very efficient for 2D geometry, you can do even better, because if you have spatial light modulator, you can do, in fact, all the potential that you want, you can create by hand. So this is for somehow real space experiment, where we look at the expansion and the atom on spatial position. But I would like also to mention that there is another very fruitful approach to study localization, which is in kick-rotor system, where here in this type you look in fact at that dynamical localization, and you can do a mapping to Anderson localization problem. And for instance, Patricia Vignolo will talk a little bit about this system where they could observe the quantum boomerang effect. Then, okay, so for the following, everything will be in real space. So, considering the study of Anderson and ultra-cold atom and disorder, there is somehow two lines of research. Either you stick to the genuine Anderson localization, that means for non-interacting particle, and then a challenge was really to address this 3D Anderson transition, which appears when you go from relatively weak disorder, where you have diffusion. You can even be renormalized by weak localization processes, but basically it doesn't change much. You have a diffusive process. And then if you cross what we call the Joffre-Regel criterion, that means you increase your disorder so much, then you can enter the localized phase. And you should insist, and also it's related to the talk of Carlo, that this Joffre-Regel criterion really corresponds to a very strong disorder regime, basically where the wave barely experiences one oscillation between it is scattered again. So this is very different from 1D or 2D problem. So this is for 3D, and of course the physics is even richer if you add disorder and interaction. So there is a lot of things. You have seen many talks already, so you can look either at equilibrium, what was named by LEAP by Thierry Jamarki, or to the kind of out equilibrium dynamics, relaxed thermalization, ergodicity, which is related to to MBL. Of course, you heard a lot during this conference. So I won't describe more here. So what we focus in the team is about this 3D Anderson transition, and the goal at the moment is really to try to pinpoint where is the mobility edge, which differentiates so high energy level where they are diffusive and low energy level here, which we expect localization. And as you see, corresponding to this Joffre-Regel criterion, you expect to be the localized state really embedded in strong disorder. So on top of it, of course, if you can, this is already quite a great deal for experiment, but the dream will be to study the critical regime. That means to study how the diffusion constant will drop to 0 when you approach here the mobility edge, and you have a critical exponent associated to that. And in the same way, if you are now in the localized phase and increase the energy to approach the mobility edge, you expect the localization length here to diverge, also with a critical exponent. And you can even dream beyond at some point to try to observe multifractality, weird things that should happen in this region. So, but at least for experimental point of view, as I said, locating the mobility edge is already quite a challenge. And so in fact, there was already some evidences of localization in 3D. So for some experiments, especially in our group in 2012, so quite a long time ago now, and also at the lens. But as I will show you and try to explain you, it's still difficult experiment. And in fact, there has been more recently numerical study where we should expect this mobility edge by numerics. And this work was done by the team of Dominique Deland. And as you will see, there is some quite large difference between experiments and numerics. So to be as clear as possible, let me show you what are the prediction of the mobility edge by numerics. Let's suppose this is the exact one. So in this graph, I show you the mobility edge here on the vertical axis, which is referred to the mean value of the disorder. That means here, this dotted line corresponds here to the average value, V0 of the disorder. And what you can see first is that the mobility edge here, which is the black line, it's always below this average value, which once again corresponds to the fact that it corresponds to a very strong disorder regime. And here it is also just on this axis, it's normalized to the average value. That means that, of course, 0 will correspond to average value, and -1, which is shown here, will be the bottom energy level here. So on this axis, it's the disorder strength. So when you increase the disorder, and it is renormalized to a very key important quantity on the system, which is called the correlation energy, which is set by the correlation of the disorder. So if you have the sigma, which is the speckled one size, of course, we do optical potential, so you can don't know better than the diffraction limit. And this is a very physical energy scale, meaning it's just the energy that you have to pay if you want to confine your particle, your wave function on the size of sigma, or let's say on a whale here on your disorder. And clearly, this was also discussed yesterday by Svitana, you can differentiate two different regimes in that. Either the parameter eta, which is the ratio between them, is much smaller compared to 1. Meaning this regime, meaning that if your potential is not able to locate a wave function in it, so you have to spread the wave function over many sites. You have a strong tunneling effect. You expect very quantum effects nature in this regime. In the opposite region, when you eta will start to be larger than 1, so you can go much further than that, then it is what we call the classical disorder regime. We expect that you have a smooth potential. Everything is basically semi-classical there. And you even expect this, in fact, mobility edge for gentle disorder kind, like for Gaussian disorder, to reach at some point the classical percolation threshold. For laser speckle, I should say that this thing is rather different because the percolation threshold is extremely low. I didn't plot it here, but if you remember the talk of Svitana, this is around 0 energy. So all in the following, there is no possibility of classical trapping anywhere in the system. Okay, classical, you can forget about this classical percolation threshold. So this is for, of course, numerics, and the experiments look like that. So I won't comment much our experiment in 2012. You see, it was in fact really dedicated. So in this graph, we don't see much in the quantum regime at the time. And okay, it seems not stupid with prediction, but I should say that it's very indirect measurement. Okay, just an estimation. In fact, it's more an estimation as a scaling. So it's not data points, it's a scaling. So it's good, but of course, it needs further investigation. And the other experiment that was done at length, so especially by the group of Giovanni Modugno, Massimo Inguscio, I should say, okay, here, if you look at the result, it's rather disappointed because it's still far away with large dispersion. But I should mention this is why it was a very nice experiment, which goes beyond to what we did at the time. But it also emphasizes that, so it's somehow less indirect or more direct measurement, I would want to see, positive or negative one. But it also highlights how difficult is the experiment. So they try to do their best, but it's still far away. So why it is so? So just to give you an insight what's difficulty of the experiment, I just show you briefly how I was looking our experiment in 2012. So here it's what you can see is ultra-cold atom propagating in disorder, so in 3D optical disorder. So we have magnetic levitation, so we don't care, of course, about gravity, and we let them expand for a while. When I say for a while, you see that the time scale here is 2 seconds, 4 seconds, 6 seconds. And if you remember the talk, for example, for Emmanuel, in optical lattices, typical time scale, they were considering it's a millisecond time scale. Okay? Here we are on the second time scale and even almost 10 seconds. So this is extremely, extremely long and difficult also for ultra-cold experiment, for ultra-cold atoms. Okay? So if you do that, then there was a good news is that at the center you see after some times, and you need to wait rather a long time, you see a localized part appearing. And this was nice because it was very first evidences somehow that you can really get this 3D Anderson localized atom. But at the same time, so that was the good news, there is also bad news. Clearly there is a dynamics, and if we look here at the wings, we could really see that there is a diffusive background at the same time. So it's like at the same time we have localized part and a diffusive part. And just to mention why we need so long time, it's just once again because the diffusion constant is going to 0 here, so it's extremely low diffusion. So it's really normal to observe something like that. So why we have these two phases at the same time? Once again, it's related to this kind of naive intuition that you can get from experimentalists, coming back to this Joffe-Regel criterion that tell you that you need really extreme disorder if you want to localize. That means you prepare your BEC, somehow in this scale, the narrow width is like 0. Okay, you have extremely low temperature, can do very nice things with ultra-cold atoms. But then you switch on the disorder. Whatever you do, you want to reach extremely strong disorder regime. And then whatever you do, you end up with a quite strong broadening of the energy, which will span across the mobility edge. We can show that, in fact, it's difficult to do otherwise. And so you have diffusive atoms here that we could see on the wings, and you have localized part. So with this and refined treatment, if you can say something about the distribution, you can still try to get indirect estimation of the mobility edge, but it is rather, it's not really precise. And you can forget about real direct observation of a transition, about critical regime or whatever if you have to do something like that. So what you have to find is find a way to have a way to control really the energy of the atoms, and ideally to set it everywhere here and look for a given energy, is it diffusive and localized and not all at the same time. So this brings me to the second part of the talk, where we develop this spectroscopic scheme to try to resolve the problem. So if you understand what I said, is that if you use a single state, somehow you create your BEC there, and then you switch your dishonor in it, then you will make messy things, whatever you do. Okay, you will have this broad energy distribution. So the trick that we want to use is now to have two states. One state that doesn't see the disorder, where we can do our BEC, very nice energy, very well controlled, whatever. And then another state where we put the strong disorder, and we want to transfer the atoms from there to there at a given energy. And in fact, we have all the tools to do that. It's quite easy. The first thing is that you have to find a way to use what we call state-dependent disorder, and you use two spin states. Let's say spin down, spin up, and Emmanuel tell you that it's quite easy to isolate this kind of state with the atomic structure. For the one we use is rubidium. So let's say that you have used two spin states, and you find a way to create a disorder which is sensitive only for let's say spin up. Then you create the BEC in spin down, and what you will do is just you do RF spin flip, like RMN, okay? You just transfer the spin down to up, and you will end up with the energy that you want. And in fact, with this kind of processes, it's very easy to show that the final energy is just the initial energy. Once again, this is very well defined. This is the BEC. And the final energy is tuned by you can tune it simply by your RF frequency. So you have a knob to choose the final energy in your system. And you can even choose what is the narrow energy, which the energy width that you address in your system by just choosing the coupling time. And if you are Fourier limiting, this is just given by the inverse, and we could verify that we can go as low as 10 Hertz, it can go even better. So for experimentalists, 10 Hertz is extremely low because you have many noisy things, so it's difficult. Okay, this value won't tell you much, but just tell you that it is roughly 2 orders of magnitude better than what we get before. Okay, so it's extremely much well defined that before. So what we have to do is to find a way to create this state-dependent disorder. So we did a first implementation of the scheme quite a long time ago now, a few years ago, which is very rough. And then we use, so remember the talk from Emmanuel, we use rubidium-87 atoms, and we have the hyperfine splitting in the ground state. So you have 2 levels which are separate in energy by, or let's say, around 6.8 gigahertz. And when we do, we shine a resonant laser light, which is close to resonant to F equal 2 here, and then much far resonant from the state equal 1. And remember, the potential is directly related to the intensity of the field, so the speckled potential field, divided by the detuning. So you see the detuning, the ratio is around 100. So basically, you end up with 100 detuning between that. So just technically, you see that here we are in the blue detune regime. Sorry, blue detune regime. The frequency is larger than the transition, and that means that ends up with repulsive potential in that case. And in this one, it's the inverse, so it is attractive one. But we can really neglect it here. And then we can simply do the transfer by RF coupling from this state to the other state. So to validate the scheme, what we did first, the first test, we try what we can say about the transfer rate. That means we fixed the RF coupling strength, and then we vary the detuning, and we look, when we change the frequency here, how many atoms we can transfer for each energy level. And this is this kind of curve, which is here normalized. And here what you have is the frequency detuning. So when you go from 0 here, we address this energy. You see when you are below 0, of course, you cannot populate any atoms. Then when you start to increase, you have the blue points here, and you have such kind of resonance, then it goes to 0. And in the red curve here, you have the numerics that were done by the team of Dominique Delorme. And here you have a perfect agreement, say, without any adjustable parameter in that. So this, as a first step, we say, okay, that's good. That means we control what we are doing here. But in fact, it's much better than that. Because if you look here, you can, in fact, calculate what you expect in this kind of system simply using the Fermi-Golden rule that tell you that the transfer rate will be basically proportional to the overlap between your initial wave function of your BEC and the final energy state here, and you have the density of state. And if you realize that in this system, in fact, the BEC is like something very uniform, very large, it's expand compared to the typical size of the system, which is that the speckled ground size, let's say, or less than 1 micron. So you can really suppose that it is like a uniform wave, and you can make this the assumption that this wave function is nothing else than k equals 0. Okay, and then this expression is nothing else than the spectral function that was discussed by Zlitana yesterday for k equals 0 at a given energy. And in fact, here, this numerical was not a numerical simulation of our scheme, but it was independent measurement with techniques which have nothing to do with our scheme to calculate directly the spectral function. And so that was very nice thing. So we spent some time to study this spectral function that I won't have time to discuss much today, but we could span from the quantum regime here to the classical regime. That was the first things, and we can say many things about scattering properties, elastic scattering time, and so on, from weak to strong disorder regime as well. Another very good thing, and this was a part, just a small part at the end of the talk of Zlitana, is that also we use this kind of spectral function to really initiate a very fruitful collaboration with Marcel, Zlitana, and Pierre, which was a PhD student, to find a new way to calculate the spectral function using the landscape. Because before, if I come back to this, in fact, there is no numerical, theoretical, numerical of course, but theoretical way, a theoretical approach to have this, to calculate this spectral function. You can do it in perturbative approach, you can do it in very strong regime, you can do self-consistent things and so on, but it's really difficult to do that. And from the landscape function, what they could do is something which is not perfect, but it's still very good and span for all regime for code. So we were happy on that. So as you can see, I could speak for a whole talk about that, but it's not the subject today. So what we want to do is, when we have transferred the atom, is of course to try to look now at the transport dynamic. Do they diffuse, localize, ballistic, or whatever? So we want to let them evolve in this order. So the one which are familiar with ultra-cold atom, maybe I've realized that this scheme, in fact, is not adapted to that. Because if you're going to have close to resonance, your wave close to resonance, then you will excite a lot of atoms in the excited state. You will have highest photon scattering rate and so on. And that means that the lifetime typically is only 10 milliseconds in this system. So remember, 10 milliseconds can be long for some system, but not for us. It's extremely short. We need seconds to see expansion. So clearly, we have to find a new way to create this state-dependent disorder if we want to go beyond. So this brings me to the last part, where we show the recent progress somehow that we have using a new kind of state-dependent disorder based on the bichromatic speckle. So the idea, if you want to increase, so I'll start back with this atomic structure. If you want to improve the lifetime, you have to increase the detuning. So let's say here I'm increasing a lot. Then it's good because the lifetime will increase. But at the same time, it's clear that you will lose the state selectivity. Somehow the detuning will be roughly the same for the two states. And here, for instance, but you will have this disorder set here, but also in state one at the same time. So we have to find a trick to kill this one. And to do that, what we are doing is we add another laser, which we call the compensating laser, which is a small intensity and which is now detuned in between these two states. For instance, for this state, it is now what we call red detune, which corresponding to attractive potential, and we can set the amplitude so that they will cancel each other. And for the other one, they will sum up, and you end up something with like a real speckle disorder. So this looks really simple. In fact, it's a bit more subtle than that. Okay, can you move on? Yeah. Okay, the point is that clearly, if you know a bit about speckle, it is clear that the precise position of the point, energy, the maxima of intensities, strongly depend on the wavelength. So if you change the wavelength, of course, you won't have exactly the same speckle pattern, and then it's not clear how you can really subtract both. So you have to pay a compromise between lifetime, the correlation, and so on. So we study quite a lot these things, and so if you're interested on this, you can look at the preprint paper, which is in the archive. And to make the long story short, we could achieve to have rather long lifetime, so which is not extremely long, but bigger than 1 second, and efficient subtraction of the two speckles. That means the residual decorrelation is rather small. So to convince you that this is working, I reproduce exactly the same kind of things as before with this B speckle here, where I compensate this one, and you see once again this perfect agreement between our measurement and the spectral function. And when we transfer for given energy state, here, for instance, we could look at the lifetime, and here we measure something which is a bit bigger than 1 second. So this is not, once again, this is not perfect, but it is much better, and then we can initiate some experiment. So we have almost everything now, so let's see what we can do. So just to make things as clear as possible, I recall the experimental procedure, even if I believe it is quite clear now. So first things, we set a given disorder amplitude with our bichromatic speckle scheme. With two speckles, we choose detuning, intensity, and so on. And for instance, I will show you first the result with eta, the parameter between V0 and E sigma round 2, which is here somehow on the right side on the graph. Then, when this is set, we transfer the atom at a given energy. Then we let it expand. We try to find out how they behave. And of course, last things, when we now change the detuning, so from 0 to higher energy, so somehow we can cross from here to large, then we expect to see something, at least we hope to see something which may happen around this critical energy with numerics. And maybe we find another one, or maybe we find nothing. So what I just want to say is that what I will show now is really preliminary data. So some are just from a few days ago. So we don't understand everything to what I show you. So of course it's a bit scary, but it's also very exciting from experimental point of view, because maybe that's the way at the time where you try to explore things, try to find out what you can say about it. And so just to let you know this. So the first curve that I want to show you is an experiment where we do this procedure, but now we let a fixed time of expansion, so rather 2 seconds in the disorder. So, and then we measure the RMS size, which is plot here to the square, which is not so important here. And we scan the energy. Okay, that means I go up like that. And as you can see here, so it is not a fit, it's just a guide for the eyes. It's quite clear that at low energy, it seems that nothing happened, or at least it's constant, and then start to grow. Here, rather linearly. We can see more detail later what will go. And then it seems that something happened around here, and then it's quite worth to compare. What is this value here? And if you do that, you end up with this, which is incredible somehow, which is exactly where is numerical prediction for this curve. Okay? So, of course, we're extremely happy with these kind of things. And then when you have it, before say, well, we have it, then of course you try to change the disorder and try to see if you eat this work. Then it's working again. Okay, then I decrease the disorder. Okay, maybe it's a little bit less messy here, but roughly constant. And then once again, the same kind of behavior. And once again, I think you understood the point, is not so far. So here, honestly, it's just there, but clearly it's not far. And once again, it's a very, very early experiment. Okay, so seems very compatible with prediction of the mobility edge. And I should say that we are very happy on that, because it's quite a long time we're struggling about that. But then a natural question arises, is it really a mobility edge? I mean, mobility, sorry, it will come. Okay. Mobility refers to, is it moving or not, localized or diffusive? That means we have to look now at time expansion. What's going on for a fixed energy going on time? So what I will look here is I stay to this value, and I will show you two curves, either for expansion for rather low or either high energy, or what we expect in the localized. So let's start in the diffusive. So here what you see is the plot for different time, okay, and expansion. So here the energy is fixed, and we just wait for time, and this is what we expect to be in the diffusive regime. So clearly it's moving, it's quite nice. You can measure the RMS, try to measure it, and you see that it's going like that. So it's a bit disappointing, it's not fully linear because it's square. Well, we can discuss that, but at least it's going. And if I want to estimate roughly, okay, experimentalist, I can do whatever I want, so I fit with a linear slope, okay, and try to extract some diffusion constant. And if I extract this, then I find a diffusion constant which is extremely around, it's like a factor 1. Here, over a typical diffusion constant, which is well known when you study this kind of trouble, which is S bar over 3m. Okay, which is typical. Of course, it could go to 0, but typical order of diffusion constant you expect just above the mobility edge. So it's exact, and you can in fact translate from this like an effective Joe-Feregel criterion, which is 1. So this is once again other very good news, meaning that the expansion that we observe is really compatible with something that you expect if you're really looking at dynamics just above the mobility edge. So that's one again a very good news, but we have to find out why is it some technical problem at the moment. I mean it's difficult experiment. We have to look at it, but it's extremely on the good side. Then, of course, what we want to see is what's going on in the localized. Do we see some localized rate function or whatever? So here, it's the same thing, and you see it's not strikingly different. Why is not strikingly different? First things, you have to realize that nothing is really moving in the system. It's moving so slow. So at the beginning, you are limited somehow the initial step of the atomic cloud. So here, what you can say, at least it seems nothing is moving, except that the part at the center is decreasing. So I'm quite sure, looking at it in more detail, so that's very recent, we will find out that there is localized fraction here. I can bet for it, it's for sure. But, I mean, for sure, I believe it strongly. But at the same time, you see, okay, it's not perfect here, but it's still expansion in the wings. So somehow something similar that what we get in the first 3D experiment. So this is maybe the more bit disappointed part. But once again, we are just at the beginning. It's not so clear if it is residual excitation of the system or it is real physics or whatever. So then I'm sure we will learn quite soon on that. So clearly this is work in progress. I don't know the time left, and maybe I was a bit fast, but here I don't want to show you more than that. I end up to the conclusion. So I hope I convince you that we have first signature to something which is compatible with the observation of the mobility edge. Of course, there is remaining question there, but we have these 2 points here, and of course, we have to continue. So it's only the beginning. So of course, we have to solve some issues that I've shown you. Is this really diffusive constant? Seems to have a rather weird behavior on RMS. Is it real physics, excitation? Maybe both of them at the same time. So we have to improve that. Of course, we would like to span more and more in this regime, and honestly, we try a bit already, and we have more difficulties here to find something when we go in the quantum regime here. And you have to realize that you have to decrease the energy. Everything gets more and more difficult for experimentalists. You have sensitive to more details, more and more and more and more. Okay, so this makes clear that in fact here, as soon as we go more and more, then it's very striking. Then it starts to be difficult. So we have to find out what we can say about that. Of course, we like to compare this with prediction from landscape theory, for sure. And you have seen that, in fact, yesterday from the talk on Slitana, that if you look somehow just at the percolation, when I say just, somehow it's very related to it. So we have also to continue this very fruitful collaboration on that. And of course, the dream will be if we succeed to have a very clear understanding on what's going on here to try to tackle this critical regime. That will be a dream for us. Well, I finish on that, and once again, I want to thank a lot the PhD student and Niro and Jan, the postdoc, which are working hard on the experiment. I'm asking a lot about data from them until yesterday, showing to it. And of course, Alain, which is following that, and all the theory friends on that. So thanks a lot.